Hello? Hello, can you hear me? Hello? Mamta madam, can you hear me? Okay. Good afternoon to everybody. Okay, thank you. Okay. Now, this is the linear algebra, 5th semester of mathematics. Already we have discussed some concept of first unit and second unit. This is the second unit. First unit is vector space definition and vector subspace definition and some other examples. Along with the examples and some properties of vector space and subspaces, linearly dependent and linearly independent of the part. Now some other examples are also well defined in the previous session. Okay. Today we will discuss what is the basis of a vector space and subspace with basis of a vector space and dimension of a vector space and finitely generated of a vector space, and along with the examples and some other properties along with the theorems. Okay. Now just you have to see here. Is it visible? Okay. Now just you have to see here. What is the basis of a vector space? Okay. First of all, we have to discuss some of the definitions. What is the basis of a vector space? Let V be any one of the vector space. Just you have to see here. You can observe very clear. Okay. What is the basis of a vector space? Let V be a vector space over the field capital F and capital B be any one of the subset of vector space. Then V is called a basis for V over F. First of all, capital B is linearly independent. Now here let V be any one of the vector space over the field capital F, and at the same time capital B be any one of the subset of a vector space, then it is said to be a basis of a vector space. That is, if the subset is linearly independent, that is the first condition. And second one is linear span must be a vector space. Linear span means L of B equal to B. Then these two conditions must be satisfied. Now that is called a basis of a vector space. This is one of the important definition and enter the part of vector space. Okay. Next, here once I have to repeat here, what is the basis of a vector space? Now, basically, here capital B be a vector space over the field capital F. B be one of the subset of vector space. Now, the subset of a vector space is called basis of a vector space. Here, the first condition is that subset is linearly independent and over the field, and second condition is linear span. What is the linear span? Now, that subset of the linear part must be a vector space. That is called the range of a vector space or linear span of a linear span means L of B equal to capital B. Now, just you have to see one of the examples. There are very two important conditions here that the subset is linearly independent, and second one is the linear span means L of B equal to B. When these two conditions must be satisfied, that is called a basis of a vector space. Now, this is one of the important definition. Now, here the briefly explanation. Just you have to see here capital B be any one of the vector space of the subset capital B is a basis for V if and only if every element of V has a unique representation. In the just V be any one of the vector space. Now that's vector space of the element is a small x B belongs to capital V. Here x belongs to V means that x belongs to V represented as, okay, x belongs to V capital V represented as a unique representation of the form a1x1 plus a2x2 plus 1 anxn. Now this is now a1x1 plus a2x2 plus 1 an. Okay, an xn with x1 in xi values, all xi values represented in vector space. Here xi belongs to capital V. Now at all the ai values are field elements. Okay, at the same time, that is the unique representation, that is the linear combination of a vector space. Now, the basic concept is the vector space itself is known as, because every vector space in the vector space is a linear combination of vectors in the bases. Now, every vector, that vector represented unique representation in the vector space, it is a linear combination. Means here alpha b, here x equals to, or x equals to summation ai xi. Now that is also a basis, because every element in the vector space must be represented as the linear combination of vector space in the basis part. Now just you have to see and refer the theorem. What is the theorem? Let capital B be a basis for a vector space capital V over the field capital F, and B contained are equal to C contained are equal to B. Now every vector space, here the given the vector space is capital V, and along the subset basis part is capital B, and there are some other bases are also represented given this part, because at the same time here the condition is B contained are equal to C, C contained are equal to B. It is linearly independent over capital F. Okay. Hello? Hello? That's enough. Now here B contained are equal to C contained are equal to capital V, and C is linearly independent over F. Then the condition is B equal to C. There are number of bases on vector spaces of the part, because here those bases of the part must be equal, because here V be any one of the vector space, and before that here the representation of the basis part is capital B, and at the same time just you have to assumption, we must have to assumption the C is also a linearly independent of the part. Now that linearly independent set and basis part both are equal. At the same time, S contained are equal to B. That is another subset of the part. Then it is the linear span and S equals to B. In other words, given the statement either this one and another one is B is a maximal linearly independent. Now welcome to Soumya Devi madam. Okay. Now this is the in other words, capital B is a maximal linearly independent set, and it is a minimal set whose linear span is V. Okay. Now this is also another one. Okay. This theorem, there are two parts. One is this is one of the parts is this is, and second one is capital B is a maximal linearly independent set, and it is a minimal linearly independent set whose linear span is capital B. Because now at the same time this question is also given. Now prove that let B be any one of the vector space, and the condition is B contained are equal to C contained are equal to B, and C is linearly independent over F. Now we must prove the B equal to C is there, and at the same time, please stay on the line. Please stay on the line. Please stay on the line. Okay, thank you. Next one, just you have to see and refer here. Okay. Now here the condition is when the B equal to C, and if when it is another basis set is also represented as S contained are equal to B is there. Now that subset is also a basis of the part when the condition is a linear span, that is L of S equals to B is there, or then automatically S equals to B. Now either this is the question is given one way is this is one, and another way is prove that B is a maximal linearly independent and minimal set whose linear span through linear span is capital B. Okay, that is that question is given. Okay, that is one of the scope here. Now another this is the proof. Then the proof of the given the statement. First of all, we must assume that B contained are equal to C contained are equal to B. That is the condition is given. And before that, let V be any one of the vector space and B be a basis of a vector space. And here condition is given part is C is linearly independent over F. Okay, since when the linear span is L of B equal to V by the definition, because what is the basis of a vector space? Now, the subset of any subset of vector space when it is linearly independent and the linear span, that is called a linear span means L of B equal to V. Now that is called a basis of a vector space. Now here the basis of this set is capital B is that is the notion of the part. L of B equal to B, that is the linear span. Now we have to assume any one of the vector is x belongs to B. We can express x as a linear combination of elements of capital B. Now that vector must be equal to summation ai xi. That is a1 x1 plus a2 x2 plus 1 an xn. That's enough. Okay. Now where all those elements are different and distinct elements given in the basis set. Now then the corresponding of the elements is ai belongs to ai values means a1 a2 so on an. These elements are field elements. At the same time b is also contained or equal to c. This is the kind of from the condition is given. Okay, that is b contained or equal to c is there. Okay. Now all the elements are belongs to c is there. Now when the at the same time given the linear combination that is when the vector must be equal to here x be any one of the element. That element represented as a linear combination summation ai xi. So x converting into this side or x is transferring into this side. We are getting the minus x is there, minus x plus a1 x1 plus a2 x2 plus so on an xn. Okay, minus x can also be represented as minus 1 into x is there plus a1 x1 a2 x2 so on an xn. Now x can be shifted at right side of this part. Okay, that's enough. Minus 1 into x plus a1 x1 a2 x2 so on an xn equal to 0. When the given the c is linearly independent, then all the elements cannot be distinct here. Now that is x must be equal to x I values. So for some I values means I equal to 1 to so on n values. Okay. Therefore, C contained are equal to B means now then automatically B equal to C is there because all the elements, all the vector space elements given the basis of the part and corresponding the another basis of the set is C is there. Now, next suppose S contained are equal to B is there. Automatically linear span L of S equal to B because already B here S contained are equal to B means already we know that B is a basis of the part. Basis from the condition from the definition of basis L of then automatically L of S equals to B. That is the linear span of this part. Suppose S not equal to B, then there is just another element. Just you have to assume the another element here. Y may be existence of this part. Y belongs to B such that Y is not consisting of S. Since here Y is also belongs to B means that Y element must be the linear span. Now we can write y equal to b1 y1 b2 y2 so on bm ym. Okay, now all the y elements are distinct elements given in the set. Yes. Okay, now all the bi values are field elements, that those elements are scalars. So here all the y elements are distinct elements. Now again we can also written as minus 1 of y plus b1 y1 plus b2 y2. This is okay. This is the set represented as a capital S. Minus 1 of y plus b1 y1 b2 y2 so on bm ym equal to 0. This is the contradiction of this part. Here capital B is linearly independent. Therefore, S equals to capital B is there. Okay, this is the one of the important theorem. Okay, next just you have to see and refer this theorem. 2.3.3 theorem is now given the suppose capital B equal to set of x1 x2 so on xn. This is the basis for a vector space capital V over a field capital F. All the elements are corresponding. The elements are all the basis elements are y1 y2 so on yn. Now this is the representative of this part. Okay. Now all the elements are, it is a linearly independent set in the B. Now here the condition is m less than or equal to n. This is the part. Suppose one just you have to repeat here. The statement is capital B be any one of the set. Now this set represented is a basis for a vector space capital V over a field capital F. Or y values are y1, y2, so on yn. It is a linearly independent set in capital V. Now then automatically we must prove that m less than or equal to n. That is the not exceeding of the elements, because m if when it is m less than n or then it is less than or equal. Okay. Now first of all let capital V be a vector space. Then the basis set is capital B. Okay. Now And here this is the set of elements. Y elements are linearly independent set. First of all, so here the condition is y values. Just you have to, one of the assumption is y1. Y1 is also consisting linear span along with the basis set of the part. Here y1 is a linear combination through the basis of the values. Basis set of values are along linear combination is S1 equal to another, we have to assume another subset is there. S1 equal to set of Y1 including X values, basis set of the values must be joined. Another element is Y1. That subset is S1 is there. Now, this set is also, it is S1 contains capital B is there because S1 is the, along with the element is Y1 of the basis set of the elements. Then it is linearly dependent because one of the element must be maybe joined here. Okay, since a set of y1 is only singleton element, y1 is linearly independent set, we get a linearly independent subset T1 of S1 such that here y1 is consisting T1 and it is contained are equal to S1. Therefore, L of T1 equal to L of S1. Therefore, since B contained are equal to S, therefore, linear span L of B equal to B, we get that L of S1 equal to B, and similarly we can prove that we can prove that L of T1 equal to B is there. Therefore, T1 is a basis for B. Here, Y1B, one of the element belongs to T1. Now, number of distinct elements in T1, it is not exceeding n plus 1. That is mod T1 is less than n plus 1. Now that maybe that value is an equivalent to mod S1 because T1 is contained or equal to S1 is there. When S1 is linearly independent and T1 is linearly independent, therefore T1 is not proper. T1 is directly contained S1, but it is not equal. But T1 includes Y1 and excludes at least one Xi values. Now consider S2, another subset is S2 equal to set of Y2 union of T1 values. So Y2 is also including the remaining the subset is the above subset is Y1. That is Y1, Y2, so on, X1, X2, so on, Xn is there. So Y2 is also, that element is also consisting of vector space. Now that is the linear span of the part. It is a linear combination of elements of T1 and S2 is a linearly dependent of the part. Students, listen carefully. Now when these two elements are linearly independent, we get again the linear independent subset is T2 is not, T2 directly contained S2, but it is not equal. Y1, Y2 belongs to T2 when that is those subsets are S2 and T2 subsets are linear span. Linear span means L of T equal to L of S2 equal to B is there. Therefore, again T2 is a basis for B. Now, similarly, there are number of subsets must be formed here. T3, T4, T3 is also contained S3, but it is not proper part. Y1, Y2, Y3 belongs to T3, and L of T3 equal to L of S3 equal to B. Similarly, L of Tm equal to L of Sm equals to B is there. Okay, therefore, it is consisting of the elements is m elements. Okay, therefore, Tm plus 1 contains Y1, Y2, so on, Ym minus 1. This is the Tm element. Before that, m values of the before of the part is m minus 1 elements. Now that subset is Tm minus 1. It is also contains at least xi values. It is a basis. Therefore, Ym is a linear combination of and of Y1, Y2, so on, Ym. This is the contradiction of this part. Therefore, m minus 1, it is less than or equal to n minus 1. Similarly, we can prove that m less than or equal to n is there. Now, this is the number of basis subsets of the part may be formed here. Okay. Students, this theorem is also very important in the final examination because this is the main part of vector space. What is the basis of a vector space and the basis of a vector space, and another one is dimension of a vector space. And before the dimension of a vector space, we must know that what is the finitely generated of this part. Okay, listen carefully. A vector space, B be any one of the vector space, when it is finitely generated, if there exists a finite set, existence of the finite set is S. Now here the consisting of the elements is set of x1, x2, so on, xn in capital V, whose linear span L of S is equal to capital V is there. Okay. Now here the finite set represented as a set of S equal to a set of x1, x2, so on, xn. Now when it is linearly finitely generated of this part, means a vector space capital V is said to be finitely generated if there is a finite set capital S equal to set of x1, x2, so on, xn in capital V, whose linear span L of S is equal to capital V is there. Okay. If V is finitely generated, means L of S equal to V, then S contains a basis. Okay. And already we have proved the above theorem is there. This shows that any finitely generated vector space has a finite basis. Very important theorem. Any finitely. Now this is also one of the fill in the blanks is there. And multiple choice, whatever it is, match the following. Finitely generated vector space. Now that is the finite basis. Finitely generated vector space has a finite basis. What is the finitely generated? If the finite set is in V, whose the linear span equal to vector space. Okay. When a vector space, when it is finitely generated, means a existence of the finite set is a set of x1, x2, so on, xn in vector space, whose the linear span is equal to capital V. That is called the finitely generated of the part, because that subset of the elements must be a finite through the vector space. Then when the linear span means L of S equals to capital V is there. Okay. L of S equal to V, then the finite set of the party also existence in capital V is there. So that is called the finitely generated part. Now one of the important bit is finitely generated vector space has a finite basis. Please note down, please underline this line. Please just open your textbooks and see the page number 17. You must be underline of this part. Finitely generated vector space has a finite basis. Okay, see the another term is 2.3.5. Any two bases of a finitely generated vector space have the same number of elements. Because this theorem is very important. Of course, this is only not necessary. Easy to say, sir. This is simple proof how to award the marks. Because here the concept is main. Because any two bases are finitely generated. You have to take in any two bases, but those bases are when the corresponding of the finitely generated vector space have the same number of elements. Suppose any two bases means either capital B and capital S, L of B equal to L of S. Already how to prove the above theorem is there. Those bases of a vector space corresponding the elements of a vector space, the same number of elements, because basis set is one of the basis set is capital B. Now n consisting of the elements given in the set, and another one C is also another basis of the set, and those elements are also x1, x2, so on, xn. Okay, or y1, y2, so on, ym, or x1, x2, so on, xm. Because n consisting elements and m consisting elements, n equal to m is there. Now that is a simple proof, because already we have proved in the above manner. Okay, capital B equal to, this is the one of the basis set. Here the elements are x1, x2, so on, xn. Okay, now that vector space should possess a finite basis. Finite basis set is finite elements of the set, means that is the capital B equal to x1, x2, so on, xn. And another basis set is capital C. C must be a finite. The number of elements in C must be equal, then must be less than or equal to n. By the same arguments, n is not exceeding of mod C, because not exceeding means n less than or equal to mod C is there. Then automatically those elements are here. N elements must be equal to the given the another basis of the set. Here and same elements are given in the basis set. So mod C is also equal to n. Same elements are given in the basis set. That basis set is capital C. Therefore, same elements are n, y1, y2, so on, yn is there. Whatever it is. Here elements are same. Okay. So same number of elements given in the another basis set. Therefore, one basis set is capital B and another basis set is capital C. Both the different and distinct elements are equal, same or equal. That's enough. Now, then the bases, any two bases of finitely generated vector space have the same number of elements. Just you have to mention the 2.3.3 statement is also there. Just you have to already this one. Okay. Now this statement just represent given this theorem. Okay, that's it. Next one, see the another definition. What is the dimension of vector space? What is the dimension of a vector space? What is the dimension of a vector space? Here, capital VB finitely generated vector space. Before that, what is the capital V? Finitely generated vector space over the field capital F. The number of elements in any basis is called, okay, finitely generated means finitely generated vector space is capital V over F. The number of elements in any basis, number of elements in any basis is called dimension of V over capital F, is denoted by dimension V or simply dimension V. Now it read as dimension of a vector space, simple notation and notated as dimension V over F, dim V over F, or simply dim V. Dim V means the dimension of vector space. That vector space must be finitely generated vector space. That is the capital V. So, which are number of elements given in the basis, that is called the dimension of a vector space. Now that is the represented as dimension V is dim V. Okay. Now see the one of the finitely generated vector space is also called, okay, finitely generated vector space. There then the elements are existence of the basis. Now that is the finitely generated. Existence of the basis set is called finitely generated. But who's the number of elements given in the basis? That is called finite dimensional. Then who's the elements when it is finite given in the basis set? That is called a finite dimensional vector spaces. Simply notated as dimension V over F. Okay, that's enough. Now see the one of the example. Students, listen carefully. See the example here. One of the example, any one of the vector space through the complex numbers or the real numbers, whatever it is. Okay, through the complex numbers of the part, dimension of C over the complex numbers, only one element is existence. Through the complex number of the basis element is only one. Singleton element is one. That is the basis for C. Only one base is here. So in examination is given the field C of complex numbers and the field Kepler of real numbers. Okay, here Kepler is a subfield of capital C. Capital C means complex numbers of vector space. Okay, over the Kepler, there are then their elements are 1 and I. Dimension C over the real numbers. Okay, C means that is the basis. That is the basis set. Basis set of a vector space. Basis of a vector space is capital C. Now over the complex numbers, that dimension is 1. Over the real numbers, that dimension is 2. Those elements are set of 1 and I. 1 and I is a basis for C over real numbers. Okay, that's enough. Now, this is one of the important example. Dimension C over C equal to 1. Dimension C over R equal to 2. This is one of the important bit is there in the exam. In the final examination, what is the value of dimension C over C? That value is 1. What is the value of dimension C over R? That value is 2 is there. Okay, that's enough. Now that is very one of the important debate in any competitive examination. Means competitive examination means either PG set or JRF, whatever it is. Okay, dimension C over C equal to 1. Dimension C over real numbers, that value is 2. Those elements of basis set is set of 1 and I. There are 2 elements over the real numbers. So 2 real numbers means 2 elements are there given in the basis set. That value is 2 over the real numbers of the part. Okay, next one. See through the polynomials, n tuples of the field elements. Yet here n being any one of the positive integer is there. Given the field is there, FB any one of the field, that positive integer is n. So n tuples of the field elements is also a vector space over F. Already that example also derived in the vector space definition. Okay. For any that I values lies between 1 and n, those elements are EI values represented as, that is the standard basis or usual basis or regular basis. Set of E1, E2, so on, En. What is the even dimension of dimension n part? E1 equals to 1. First element is 1. Remaining elements are all zeros. E1 means 1, 0, 0, 0, so on, 0. That is the even part. E2 means the second coordinate is 1. Remaining elements are 0. 0, 1, 0, 0, so on, 0. So what is the En? 0, 0, 0, so on, 1. These elements, these standard basis is always a basis set. Okay, set of E1, E2, so on, En is dash a basis set. Okay, for n tuples of the field elements. So what is the dimension? Dimension of this part? Dimension n tuples of the field equals to whose the number of elements are given the basis set number of elements is n. So that dimension is n is there. Okay, suppose n equal to 2. So dimension of 4 2 means that value is 2. Dimension of 4 2 means E1 E2 is there. Set of 1 0 0 1. There are two basis elements. Okay. Dimension of power 3 1 0 0, that is E1. E2 means 0 1 0. E3 is 0 0 1. So dimension of power 3 equals to 3. Similarly, dimension of power n equals to n is there. That's enough. One of the important bit is there. Okay. Now, see this one. Any linearly independent set in V, has at most n elements, and any spanning set is such that L of S equal to V have n linearly independent elements. See this one of the important theorem is, this is the theorem, not definition. What is the theorem? V be any, please note down, this is not a definition, this is theorem. 2.3.9, please note down, very, very important in the final examination. Let capital V be a finite dimensional vector space over the field capital F. Any linearly independent set in capital V can be extended basis. Can be extended to a basis. What is extended to a basis of this part? Finite dimensional vector space. Simply FDBS. FDBS means let capital V be a FDBS means finite dimensional vector space over the field capital F. Then any linearly independent set in capital V can be extended to a basis. Okay. See the proof. Let first of all, what is the linearly independent set? Set of y1, y2, so on. Sorry, x1, x2, so on, xn. That is a linearly independent set in capital V. Suppose m is less than or equal to dimension V over F. Here m being any one of the element. Those elements cannot exceed the dimension V over F, because here L of A not equal to V. That is not a basis, means that's not from a linear span. Then there exists an element. Existence of the element is xm plus 1 is also belongs to V. When the xm plus 1, it is not a linear combination of elements in the capital A. Therefore, set of x1, x2, so on, xm and xm plus 1 is linearly independent. If this is not a basis, because exceeding element is xm plus 1 is there, which is not a linear combination, means suppose xm plus 1 equal to, no, that element is an equivalent to write the linear combination of this part. Xm plus 1, xm plus 2, so on, xn. In between x1, 2, so on, xn, that is xm plus 1, xm plus 2, so on, xn in capital V. So then automatically set of x1, x2, so on, xm plus 1, xm plus 2, so on, xn is a basis for capital V is there. Okay, that's enough. See the examples. These examples are also very important in the final session. Prove that any linearly independent set in any vector space does not contain the zero element. It's very simple. This is the one of the short answer. Short problem is there. Now the question is short answer means that is the for 5 marks part. Prove that any linearly independent set Any linearly independent set is denoted by capital S. Okay. Suppose it does not contain the zero vector. Before that, it is zero vector is consisting of the linearly independent set. Zero belongs to S, or it read as zero is in S, or zero belongs to S, whatever it is. Suppose zero can also be written as 1 into 0 equal to 0. By definition of linearly independent, we should get that 1 equal to 0. So 1 equal to 0 is it true or false? Hence, f equal to only generated 0. It is a contradiction. Then it is a contradiction. Therefore, 0 does not contain linearly independent subset. Linearly independent set. That's one of the important part. Second one, let V be a vector space of dimension n. So dimension V equal to n is there. What is that? Linearly independent set in V with n elements is a base. N elements of the dimension of the vector space is there is a basis. That is the theorem. Linearly independent set in V with n elements, it is a basis. So basis set is denoted by capital B. Now then it is a linearly independent in B. If the B is not a basis, L of B not equal to V is there. Hence there exists xn plus 1 belongs to V, which is not a linear combination of x1 x2 so on xn. So that a set of x1 x2 so on xn plus 1 is a linearly independent. This is the contradiction because here exceeding element is also there. So then it is not a linearly independent. So then it is a contradiction is linearly dependent of this part. Okay. Now here the linearly independent set is capital B and it is not B. Suppose if B is not a basis, then it is not a linear span. Suppose here any one of the element is existence given in the basis set, then you have to write it is not a properly not a linear combination of given the basis set of the elements. So it is not, when it is not a linear combination, then it is not a, then it is a elements of the set is linearly independent. That is also contradiction. Okay. See this another one. There are three vectors is given x1, x2, x3. Three vector elements are given. E1 is 3, 1, 0, 0. E2 is 0, 2, 0, 2, minus 1, 0. And x3 is the 0, 0, 0, 4. There are three vectors is given. And these three vectors means these three elements given in the set, then it is linearly independent. Given the linearly independent means, first of all, you have to write the linear combination given for the given vectors a1 x1 plus a2 x2 plus a3 x3 equal to 0. Now, plus first of all, what is the 0 means? Zero vector means 0, 0, 0, 0, because given this element represented as the 4 dimension of the part. 4 coordinates is given. So now we must write 0 vector 0, 0, 0, 0 is there. Now a1 of x1 is just note down the x1, x2. We are taking the sets a1 of x1 plus a2 of x2 plus a3 of x3 equal to 0 vector. So that's enough. 3a1 equal to 0, a1 equal to 0. That is a1 plus 2a2 equal to 0. Therefore, a2 is also 0 because already we have derived here a1 equal to 0 and a2 equal to 0, a3 equal to 0. Each and every scalar must be 0. Therefore, given the set is linearly independent. That's enough. Now, in the same manner, second version is also there. Second, another method is there because these given the vectors must be arranged in the matrices of the form. First row, second row, third row. That is the first row 3, 1, 0, 0, second row 0, 2, minus 1, 0, third row 0, 0, 0, 4. Or either rows are row wise or column wise, whatever it is. Now to find the determinant of the part. Now determinant in the mod A. Okay, mod A means this is the 3 by 4 matrix because 3 rows and 4 columns is there. Then the order of the matrix is 3 by 4. Okay, so each and every one is 0. That's why to find the determinant of this part, when the determinant not equal to 0, by given the set of vectors is linearly independent. When the determinant is 0, the given set of vectors is linearly dependent. So that is the another method of this part. Okay. Now in the same manner, it is when the given the set of vectors, when the determinant of the part not equal to 0, it is completely depends upon the rank of the matrix. Okay, then the rank of the part is therefore because matrix of the order is 3 by 4 is there, but for fourth row is also exceeding of the given this order of the part. Therefore, one column is deleted and 3 by 3 is there. To find the determinant, that determinant not equal to 0. Therefore, matrix of the rank is 3 is there. That is the simple one. When let V be a finite dimensional vector space over the field capital F and W be a subspace of V. Any two finite dimensional vector space capital V, then their dimension is dimension V. W be a subspace, then the dimension is dimension W. When the both are equal, prove that V equal to W is there. Okay. First of all, so you have to write the dimension V equal to N is there. And in the same manner, dimension W is also N is there. Capital B equal to set of x1, x2, so on, xn. That is one of the basis set. And another basis set is y1, y2, so on, yn. That is also a basis for capital B and W respectively. This is those bases belongs to the capital B, and another one, this is the basis set is also belongs to W. Because when the W not equal to V, therefore L of C not contained are equal to W contained are equal to V. If there exists an element ym plus 1 belongs to V such that ym plus 1 does not consist in L of C, the set of y1, y2, so on, ym plus 1 is linearly independent set. Therefore, m plus 1 is not exceeding of n of this part. So, when given the both subsets are equal, so that is also a linearly independent. Then that is the contradiction of the part. So, dimension W equals to V. Okay. When then automatically vector space and subspace also must be equal. See the next one. In the polynomial function, set of all polynomials is not finitely generated because there are so many polynomials f1 of x, f2 of x, 1, fn of x. These are all these polynomials are all belongs to capital F of x. But choose an integer, MBA in one of the integer, degree f of x or degree fi of x less than m, because I lies between 1 and n. Okay. Therefore, here x power m is an element in f of x, and x power m is not a linear combination because polynomial function represented as a1 x power 1 plus a2 x power x square plus and a3 x cube plus 1 am x power m. So x power m is not element in the f of x is there. So then it is a contradiction. Okay, now because degree f of x is less than m. That is the given the set of all polynomials is not finitely generated. Okay, see this one, next one. This theorem is also very important. That is also the above theorem is also same repeat. It is briefly explained here. That's all. Okay, this is the end of the part. This is the second unit. Okay, see, please wait, see on the line. Wait, please stay on the line. Next one, what is the quotient space? Yes. Please stay on the line. Just see here. Here one of the define vector space. Give an example with briefly. This is also one of the question. And define finite dimensional space and the basis of a vector space. Prove that if V of f is not finite, if V of f is a finite dimensional vector space, then there exists a basis set of V. This is one of the important theorem in the examination that is also given along with the definitions. First of all, so define vector basis of a vector space, finite dimensional space, and prove that if V of f is a finite dimensional vector space, then there exists a basis set of V. That is one of the questions in the examination point of view. Okay. Next, see the next one. Define linear span. This is the linear span definition, and the next one is linear. Along with the linear span, one of the theorem is given. Okay, S contained are equal to T means implies L of S contained are equal to L of T. Second one, L of linear span of S union T equal to L of S plus L of T. Already you have explained here. Next one, define quotient space. Listen carefully. This is the unit 3. Okay. Define quotient space. This is the third unit. Students, listen carefully. Very important definition. And at the same time, before the quotient space definition, what is the quotient set? Just you have to see the one of the part. Please stay on the line. This is the quotient space definition. What is the quotient space? And before the what is the quotient set? Okay. See your textbooks. That is the third unit. Quotient set definition means the set of all left cosets or the set of all right cosets. Okay. The set of all left cosets or the set of all right cosets of W is in V. Suppose capital V be any one of the vector space, W be a subspace of vector space V is there. But W is in V means along with the vector space elements through the subspace may be formed either left cosets or right cosets. So left cosets means alpha A plus X plus W or Y plus W, Z plus W, whatever it is. Or at the same time, alpha plus W, beta plus W. Okay, so that is also these are all left cosets. When the vector space elements must be expressed along with the subspace of the element when it is left side, those are all left cosets. At right side, those elements are called right cosets. W plus alpha, W plus beta, W plus gamma, or W plus X, W plus X1, W plus X2, W plus X3. These are all right cosets. So the coset elements are either left cosets or right cosets given the vector space of W is in V, that is called quotient set. That quotient set must be form a vector space. Okay, the set of all cosets, of W is in V to form a vector space. That is called quotient space. Okay, and before that, what is the quotient set? At the same time, the quotient means either, listen carefully, quotient space or factor space or the set of all residue classes. There are three types of names. Okay, the quotient space or factor space or the set of all residue classes of vector space. Now there are three important similar names of quotient space. Okay, from the definition of quotient set, that quotient set of the elements are either left cosets or right cosets. Now here the cosets elements is denoted by W plus alpha, W plus beta, W plus gamma. But in your textbooks, W plus X, W plus Y, W plus Z, these are all right cosets. At the same time, alpha plus W, beta plus W, Z plus W, these are all left cosets. Okay, when any properties of cosets are there, okay, just please stay in line. Then after that, any two right cosets are equal. W plus alpha equal to W plus beta or alpha plus W equal to beta plus W, if and only if alpha minus beta belongs W. That is the subspace of condition. Okay, any two left cosets are equal, then the if and only if alpha minus beta belongs W. Any left coset or any right coset of W is in V means vector subspace of a vector space W plus alpha equal to W. In the same manner, in the group theory, just you have to observe in the group theory part. Okay, HA equal to capital H, HX equal to capital H. Either every right coset and every left coset must be a subgroup. HX equal to XH equal to H is there. That is one of the definition. And at the same time, here W plus alpha or alpha plus W equal to W. Every left coset or every right coset must be a vector space. Capital V is there. Okay, that's enough. So any two left cosets or any two right cosets either disjoint or identical. Just to see in your textbook from the beginning, some properties are given. Okay, what is that? X plus W intersection, Y plus W. That is the meaning of any two left cosets or any two right cosets either disjoint. Means X plus W intersection, Y plus W equal to 5. ORR equal means x plus w equal to y plus w. That is one of the important property on vector on quotient set. Okay. Now see this one. These three terms are the union of all right cosets, the union of all left cosets. Okay, is a vector space. That's a simple representation. Okay. So finally, the set of all left cosets or right cosets form a vector space with respect to vector addition and vector under scalar multiplication. Suppose vector space definition, from the definition of a vector space, V under addition there is an abelian group. Second one, scalar multiplication holds good. Third one, distributive law holds good. Any two conditions are satisfied in distributive law. So at the same time, those left coset set or right coset set to form a vector space. Okay. Now, what is the quotient space? Let W be a. This is one of the important concepts. Let W be a subspace of V of F. Then the set of all left cosets or all right cosets of W in V is denoted by V by W. So quotient space is denoted by V by W equal to set of W plus alpha such that alpha belongs to capital V. So W plus alpha is there, W plus beta. For all beta belongs to capital V, whatever it is. Any right coset or any left cosets. That set, that quotient set is called quotient space with respect to vector addition and scalar multiplication. Okay, that's enough. So V by W, B under addition and multiplication form a vector space. At the same time, quotient space to form a vector space. V by W comma plus comma dot to form a vector space. That's enough. Okay. Now, first of all, V by W under addition is an abelian group, and V by W under multiplication is a scalar multiplication holds good. Now, that is also one of the theorem. Okay. Please stay on the line, just see and refer. Now, this theorem is also very important. Dimension V by W equal to dimension V minus dimension W. Now, without this one, you can't expect the final examination paper. This is one of the important question or important theorem in the vector spaces. Okay, this is the third unit. Don't forget this one. Okay. Now, here V by W under addition is an abelian group. V by W under multiplication, scalar multiplication holds good, and the distributive law holds any under quotient set elements. Okay, with respect to vector addition and scalar multiplication. So at the same time, abelian group means first one closure law, associative, identity, inverse, commutative. Now all these properties are satisfied under addition. So V by W under addition is an abelian group. Okay. Along with the elements are W plus alpha, W plus beta, W plus gamma, whatever it is. These are all right cosets. Say the right cosets are left cosets means alpha plus W, beta plus W, so on. Okay, that's it. Now, here, third one, what is the zero element? Okay, what is the zero element? W plus 0 bar equal to 0 bar plus W equal to W. Okay, now that is the zero additive identity is there. W plus alpha. Okay, alpha plus 0 bar equal to 0 bar plus alpha equal to alpha. At the same time, W plus 0 bar equal to 0 bar plus W equal to, that is W. So that is the additive identity of this part. Okay, that's enough. Now at the same time, next one, existence of inverse. Okay, when the W plus alpha, W plus of alpha plus of minus alpha means W plus 0 bar. Okay, that equals to W is there. That additive inverse is there. At the same time, commutative property is also satisfied. W plus alpha plus W plus beta equal to W plus beta plus W plus alpha. That is a commutative. Simple. V by W under addition is an abelian group. Scalar multiplication. Okay. What is the scalar multiplication? Scalar multiplication means W plus A alpha equal to A plus of W plus alpha. Okay. A alpha is the scalar multiplication. Okay. W plus A alpha represented as A of W plus alpha. That's enough. Okay. Next one, the last but not least here, that is the distributive properties are satisfied. Okay, any two distributives from along with the condition. Okay, therefore V by W under addition, under addition is an ability group, scalar multiplication holds good, and the third one distributivity holds also good. What is the distributivity property? Now there are four conditions are there. Okay, what is that? Please tell me. A of x plus y equal to ax plus ay. Therefore, W of a plus of x plus y. A of W plus of x plus y. Okay, that's enough. So that is W plus ax plus W plus ay. That's enough. That is one of the condition. And W plus 0 bar equal W plus of W of alpha plus 0 bar equal to W plus alpha. Okay, that is the simple concept of conditions. Okay, now vector identity is also there. What is the vector unit element? 1 of alpha into 1 equal to alpha. At the same time, W of W plus W of alpha 1 equals to 1 of W alpha. So that is a simple expression. So W of 1 alpha equals to W plus alpha. Simple condition. Okay, any distributive conditions are satisfied. Any two distributive conditions are satisfied. Therefore, then automatically V by W under addition, under multiplication form a vector space. Please stay on the line. And that is the theoretical concept. Okay, when the quotient space, hello, when the quotient space to form a the set of all cosets or the set of all cosets to form a vector space. Now that is called the quotient space. So it is denoted by V by W. So what is the V by W element? The set of W plus alpha, W plus beta, whatever it is, for all alpha belongs to capital V. That is called the quotient space. It is that is then according to the definition. Now we must derive the one of the theorem is dimension of V by W equal to dimension V minus dimension W. Now this theorem is also very important, students. Now already time is over. Now please stay on the line. Okay. Now this theorem is also one of the important theorem from the definition of this part. Okay. Now this theorem is very, very important. The set of here W be any subspace of vector space over the field, then the set of all cosets of W is in V denoted by V by W equal to set of W plus alpha. For all alpha belongs to V is called quotient space or quotient set. Dimension V by W equal to dimension V minus dimension W. Okay, this theorem is very important. First of all, just you have to see and refer this theorem. First of all, what is a finite dimensional? When the dimension must be a finite, that is called finite dimensional of the part. Here, finite dimensional vector space is short form as FDVS is there. Okay, V is a finite dimensional, and W, then the vector space is finite dimensional, then automatically subspace is also a finite dimensional. And then first of all, you have to form the basis set is capital B equal to set of alpha 1, alpha 2, so on, alpha m. This is the basis of W. So here this is the basis set of subspace. Subspace of the dimension is say M is there. Since the set capital B is, this is the basis set. When it is basis, then automatically that set is linearly independent and it can extend to form a basis. So let the set capital S equal to set of alpha elements alpha 1, alpha 2, so on, alpha m, and including beta values, beta 1, beta 2, beta k, okay, beta l. This is the basis set of V by basis set of vector space. So here this is basis set is capital B. The basis set is represented basis of subspace. Here m consisting elements given in the basis set, then the dimension is m. At the same time, extended to form a basis means already that is basis set. Subspace of the basis set is this is, and all the elements including with the beta values, this is the base. Subspace is also defined from vector space. So when the alpha values must be including the beta values, this is the basis set of vector space. That is m values and l values. That is m plus l. That is the dimension of a vector space is m plus l elements given the basis set. That is denoted by capital S. Now, dimension V minus dimension W means m plus l minus m. We are getting the values, l is there. Now, we shall prove that the set here S dash equal to another set is also S dash. This is the V by W. V by W means quotient space set is denoted by, basis set is denoted by S dash. Quotient space elements are W plus beta 1, W plus beta 2, so on, W plus beta L. This is the V by W basis set. So then here the number of elements is L elements. So V by W of the dimension is L. Okay, that's enough because quotient space of the elements are right cosets. Okay, now here the extension of the element is beta. Now corresponding the beta value through the cosets W plus beta 1, W plus beta 2, so on, W plus beta L. That set is denoted by S dash. This is the basis set of V by W. So here consisting of the elements is L. So here the dimension of the V by W quotient space dimension is L is there. Okay. Here, first of all, we must prove that S dash is a, what is that? S dash is a basis set. Means S dash is linearly independent and linear span. Linearly independent means first of all you have to write the linear combination. At least one of the zero vector is zero vector of V by W is W. Okay. Now that is also one of the property. Any W plus 0 bar equal to W. That's enough. Now here W plus beta 1, W here V1 of W plus beta 1, V2 of W plus beta 2, so on, BL of W plus beta L equal to W. Okay, this is the basic property. Say this is the first condition. Now this is the scalar multiplication through the coset element. This is the right coset because subspace of the element at right side, that is the right coset. So W plus B1 beta 1 plus W plus B2 beta 2, so on, W plus BL beta L equal to N. So W plus of B1 beta 1, B2 beta 2, so on, BL beta L equal to W. So this is the entire the element is also consisting of subspace. So here W is a linear combination of elements of beta. So first of all, you have to write the linear combination B1 beta 1, B2 beta 2, so on, BL beta L equal to A1 alpha 1, A2 alpha 2, so on, AM alpha M. So all the elements converting into this side. Okay. Now B1 beta 1, B2 beta 2, BL beta L minus A1 alpha 1, A2 alpha 2, so on, AM alpha M. Now this is all the linear combination of linearly independent set equal to zero vector. So each and every one is zero. Each and every scalar must be zero. Therefore, given the set is linearly independent. Since S is a L of S dash equal to V by W, this is the linear span. Given the set is S dash, that is the V by W basis set is S dash. Now, what is the linear span? From quotient space, L of S dash equal to V by W. So, therefore, any one of the vector must be arranged, must be equal to the sum of the linear combination of the part in overall the elements. C1 alpha 1, C2 alpha 2, so on, Cm alpha M, plus D1 beta 1, D2 beta 2, so on, dt beta t. All the C values and D values are field elements, and enter this part is an equivalent to gamma plus D1 beta 1, D2 beta 2, so on, dk dl beta L. Gamma is C1 alpha 1, C2 alpha 2, 1, Cm alpha m. So this is the linear combination of beta. Okay, here alpha belongs to capital B, and therefore W plus alpha is also belongs to B by W. Therefore W plus alpha equal to W plus alpha means just note down gamma plus D1 beta 1, D2 beta 2, so on this one. Finally, W plus D1 beta 1, W plus D2 beta 2, so on W L of that is what is that? Here W plus and DL beta L. So here D1, all the scalars must be separated from the coset element, coset multiplication. Coset, what is the coset multiplication? W plus A alpha equal to A of W plus alpha. That is the scalar or coset scalar multiplication. Vector addition is W plus alpha plus W plus beta equal to W plus of alpha plus beta. Okay, that's it. Simply W plus alpha belongs to L of S dash. Therefore, finally, L of S dash equal to W plus alpha generated. So the generated element must be range of the element. So that is linear span L of S dash. Finally, L of S dash equal to V by W. Therefore, S dash is a basis of, therefore S dash is linearly independent and the linear span. Then automatically S dash is a basis of V by W. Finally, dimension V by W equal to, what is the V by W dimension? L. L value is equivalent to dimension V minus dimension W. That's enough. Students, this is the end of this proof. Tomorrow we will explain another one, another important dimensional theorem, dimension of the, hello. One of the important theorem is there. Okay. Tomorrow we will explain here. There is no problem. Dimension W1 union W2 equal to dimension W1 minus plus dimension W2 minus dimension W1 intersection of W2. Now that is also one of the dimension theorem. Tomorrow we will explain here. There is no problem. Now this is one of the important theorem on quotient space. Quotient space to form a vector space. That is one of the theorem. Second one, dimension V by W equal to dimension V minus dimension W. These two theorems are very important in the final examination. Okay. Any problem? Any doubt? Students, any doubt? Hello, Mamata. Hello, Mamata madam. Hello. Any doubts? Okay. Thank you one and all. Wish you all the best and wish you good luck. Tomorrow we will meet again. Same timing, same class. Okay. Tomorrow we will explain more some other theorems also. Okay. Thank you one and all. Bye. Okay, thank you.